will at the end of the hour. So with 11.3, remember, we're talking about the geometric sequence. Geometric sequence is a little bit different. You've got your first term times some rate to the n minus 1. The easiest way to figure out your rate is always to take the second term divided by the first, third term divided by the second, and so on and so forth. That's going to give you your ratio. Basically, you're looking for your ratio. So you would do 27 over 81. Does that equal 9 over 27? Does that equal 3 over 9? Does that equal 1 over 3? Hey, I bet you they all equal a third. Wow. Crazy. What do you think your rate is?
I'll take you out on a third.
1/3. So your nth rule would have been first term times the rate of 1/3 to the n minus 1. Okay? Like I said, working with these things are going to be very, very simple to start out with. It's very easy to distinguish geometric and arithmetic sequences, the differences between the two, because here is just that constant rate of change, or not constant rate of change, constant multiplier going through. The weird part thrown in with these things comes into play when you're dealing with the following problems. When we had ones where you had two separate terms, yeah, like this. Where you had two separate terms within a geometric sequence, you wanted to write the rule. Now when you do this, you're basically solving a system of equations, but you're solving it that doesn't have an addition or subtraction. You're going to solve it via using substitution. Okay? So what we always do is we always write out our nth rule for both of them. And then filling in the blanks. I know that I have the second term in my sequence, which would be the first term to the r to the 2 minus 1. And what is the second term? So 45 equals a sub 1 times r to the first power, because it's 2 minus 1.
Oh gosh.
Wow, that was weird. Can't see what I'm doing. I probably should get new glasses. All right. And I do the same thing with the secondary equation. I know that I have the fifth term be the first term, and then fill in the blanks. That's what we bad for. Okay. Now, we have two equations with two variables. The easiest thing to always do is take one of them that has the lower degree value of r and solve that one for a sub 1 for your first term. Because you'll substitute that to the second equation. Since this is a sub 1 times r to the first power, if I divide both by r to the first, I get 45 over r to the first is my first term. And I just take that and substitute into the other equation. So you have negative 1215 is 45 r to the first, r to the fourth. And now you start playing your power rules. Exactly. R to the first, I'm sorry, r to the fourth over r to the first gives you what? R cubed. So you have negative 1215, 45r cubed. Oh no, what do you do to solve this problem? I am so afraid.
Cry.
Get
12. Get pink eye and go home someday.
Yeah. Divide by 45 and what do you get? 27. Is it positive? So it gives you the cube root of negative 27 is negative 3. Now you know your rate. What are you going to do to find your first term?
Plug it in.
Substitute back in. So there's your first term. There's your rate. And there's your term. There's your setup. It's that fast. Okay. And I know most of you guys probably did those already, so it probably wasn't so bad. I just wanted to take a quick second just to revisit how you set up the system of equations on those. Really, the biggest thing you're going to screw up is when you write down the problem, you forget to put a negative in. That's probably about the worst as it gets. Just be careful when you're writing it out. Okay? We got Hope.
What is the AM center? What it in the problem?
Oh, this is the generic. This is the nth rule. This is the rule for it all. When I put it all back together, it's to write the rule that has the second term that was 45, the fifth term that's negative 12, 15. The rule was negative 15 times negative 3 to the n minus 1. You're writing out the nth. Because remember how we did that with the system before? And now it's just a geometric way of doing it versus the arithmetic. So when you have to do it this way, geometric, you're doing substitution. When you did it arithmetically, you're doing elimination. Then the other one where you had to worry about the sums. The sums of the geometric series. The sum of a geometric series was always going to be your first term, 1 minus your rate to the n, over 1 minus your rate. And as long as you know your rate and however many terms you're trying to find, it's very, very easy. It's just a lot of substitution. I recommend using your fraction bar for these types. The goofiness lies on, yeah, am I right or am I right? Uh-huh. The goofiness in these things come into play when you have to solve for your exponent. Okay? That's about as goofy as this one can get. So let me walk you through a full problem with this. We have a geometric series of 1, 5, 25, 125, and so on and so forth. We want to find the sum of the first 10 terms. So we have to, according to our sum formula, the only things we have to figure out are, well, what's our first term and what's our rate? We do know the first term. What is it? 1. It's nice that it tells you. First term is 1. And what's your rate? 5. Rate is 5. So the sum of however many it was. First term, 1 minus r to the n over 1 minus r. Fill in the blanks. Sum of 10 is 1 times 1 minus 5 to the 10th over 1 minus 5. Now, this chapter is so dependent upon formulas, which means you need to know your formulas. So, bless you. Here's what I normally have always done. I generally give you a 2-part test. First part, matching.
Oh, that's easy.
Okay.
You say that now. Right. You say that now.
No, because what if you get that wrong? So what I do with the second part is I don't tell you which formula is which, but you'll at least have them all written out correctly.
Okay.
Does that make sense?
I remember. By matching, would you like
Which one is the sum of an infinite series? Which one is the sum of a sequence? Would that be? Yes, sir. 5? Yes, ma'am. Yeah, I plan on it. So when you put this all in the calculator, use a fraction bar. Do you need to worry about the 1 in this case? No. Sometimes you're not gonna start at 1. You go start at some other weird number, so then you can worry about it. If you put that in the calculator exactly the way it's written, what do you get for your sum of the first 10? Was it like 2, 4, 4?
2, 4, 4, 1, 4.
4, 06. You get something like that.
If it goes by 5,
You okay then?
Wait, what's the fifth?
Yeah.
We haven't gotten it yet.
You add 1.
Oh, okay. I was going to say.
Now,
Wait, you start with the 1. Oh, it's the sum of it all. Yeah, but if it goes by 5. 5 plus 1 is 6.
now the weird one. The weird part of this is when you have to figure out how many you have to add together to have it equal 3906. So what you're trying to do is figure out the end value. So you have your sum equation still, the sum of however many. It's going to be your first term. 1 minus r to the n over 1 minus r. You knew that the first term was 1, and you knew your rate was 5. So we want to know that 3906 is 1 times 1 minus 5 to the n over 1 minus 5. Once again, in this case, does this 1 out in front of the parentheses have anything to worry about? No, so I'm not going to worry about it. So I break it apart into smaller chunks. What's 1 minus 5? Negative 4. So is it okay if I erase this real quick and write negative 4?
Yes.
Exactly. I'm going to undo dividing by the negative 4 by multiplying both sides by the negative 4 then. So let's see, that's a 24, 6, 1, 14, negative 14, 6, 24?
15.
Okay. So I have that on the one side, and then on the other side is just going to be 1 minus 5 to the n. You okay with that?
Yeah.
Sir?
I think I missed something when I was writing something down. But what did the 4?
It was 1 minus 5 in the denominator.
Oh.
I just simplified it because I had to get rid of that denominator. Okay. Now, if there was a number out in front of the parentheses, I would have multiplied by the reciprocal in that case, but that happens once in a while. So now, in order to solve for n, I need that its base to be positive, because I got to take a log base. So what I'm going to do is I'm going to add 5n to the left, and I'm going to add 15, 6, 24 to the right. So I get 5 to the n is 15, 6, 25. Sure. Still got to add and move it around.
Yeah.
Remember the properties of logarithms. To get this to drop, we take the log base 5 of 5 to the n is n. And I got to take the log base 5 of this.
6.
And you get 6. Alpha Window 5. Remember, it's the name of my band? The Alpha Window 5s?
Kind of music you guys do.
Radical style. Can you only imagine it?
Oh.
I'm sure it would be far out.
We have a lot of fans that root for us.
Nice.
They must be imagining.
This fame grew.
I'm gonna quote, our fame grew exponentially. There's no point in this problem.
All of your fans are
Again, the biggest mistake you guys are going to do when you're trying to find n for this style problem is you're going to try and do too much of it at once in your calculator, or you're going to forget about the negatives about adding things back and forth. None of it yet.
And then with like the x equation, there's 2 of them, right?
Some of it, some of the arithmetic and some of the geometric.
And then we know how to use this one to get a plus sign.
It says, yeah, because that's your sums.
But will be arithmetic.
You have to figure that out. Usually it's told. You're told it's arithmetic or geometric. If you have to find the n such that this is an arithmetic or n such that this is geometric, you have to know that. So then that leads us to the last little bit of this chapter, which is the sum of the infinite. Oop, I just want to add a little here.
Just go back to the
You know, why can't we go back to like the second grade math?
And what happens with the infinite,
By-
as n gets larger and larger and larger, you get a very simple formula. And I think you guys got to watch some of this when you were
Oh.
Yeah.
You did it. You did. I told you to do it.
Yeah, he did.
because it's the gift that keeps giving.
How many is there?
It's infinite. It just goes on and on and on.
No, because
You just
Yeah.
stop.
You get an infinite. You get an infinite. Anyway, so as n in a finite geometric series gets larger and larger and larger, it approaches this value. And what I plan on doing, maybe tomorrow, if we have a little bit of time for it at the end, I'll show you there's actual proof of why it works. I just didn't want to worry about it so much today because we got a bunch of other stuff to talk about. The easy way to tell whether or not this is going to be an infinite series versus the arithmetic or geometric is that the formula just has S. It doesn't have S sub n. It's just S. It's just your first term divided by 1 minus your rate. It's all, yeah, it's really easy formula. The only thing you have to be cautious of is that your absolute value of your rate has to be smaller than 1. If it's greater than 1, it doesn't work. There's no sum. So the problems we were just doing there a second ago, we had a rate of 5, and we had to find the sum of so many terms. There's no infinite sum to that problem because the rate is too large. Okay? So the rate has to be less than 1 in order for it to work. Okay? So it's really the only thing you have to be careful of. That's why I say pay close attention to R. Okay? If the R has the absolute value that's greater than 1, there's no sum. Done, go to the next problem. Okay? So these problems look somewhat like this. Find the sum of the infinite geometric series. Again, it's in summation notation, and it has the infinity on the top. There's no infinity button on your calculator, guys, so you have to know what that means. So that means that 3 is your what? First term.
First term.
3 is your first term. Excuse me. Water. And then are we going to have an R value that's greater than, or excuse me, less than 1?
Yes.
Yeah. So what do you do? So your R value here is 0.7. So your first term is 3, and your R value is 0.7. So all you have to do is take first term and use the fraction bar. And there's your answer. 10.
Wait, what's the I?
Starting at first term. Remember, so summation, I think it's just like X, it's just summation. You're starting at first term is.
So the sum of that is 10.
Yeah.
If it's infinite, how does that work?
I'll show you the proof of it. I'll show you the proof. It's weird. It's a kind of a long-winded proof as to why this works to this. It's because as n gets large, it gets infinitely closer. So what happens is that your values wind up simplifying out.
Oh.
Okay. Because it's getting closer and closer and closer to 1.
Never actually.
Right. It's just in
9.9.
And it only works when R is less than 1. That's how it works. Or absolute value.
There's like a number value.
So if I want to find the sum of this series, is this a finite or an infinite series? Why? Because of dot, dot, dot. So what do you have to figure out? First term and your rate. What's your first term? What's your rate?
-1/4.
Negative 1/4. Is negative 1/4 have an absolute value less than 1?
Yes.
Yes. So use the formula. Sum, first term, 1 minus your rate. Use the fraction bar, parentheses, and all that fun stuff. Press. What do you get then? 0.8, 4/5. Yep. There you go. If it gives you fraction or decimal, probably gonna use decimal. So obviously the only other little bit here when you're looking about the sum problems is that if you look at the formula itself, how many variables are there?
2.
3 of them, right? So you can be given 2, solve for the third, right? Okay.
Are you gonna do it now?
No.
He doesn't have.
I could give you the sum in first term to find the rate. I can give you sum in the rate to find the first term.
What if you just give us the rate or the sum or the first term?
Then you can write it in term. You'd have to know 2 parts within it, and then you'd have to do systems. We don't do that.
It's too much work.
It's not that it's too much work. It's just we just don't do it. So let me give you some problems out of 11.4. Yeah.
Just for
I'm gonna get 11 through 11.4 from you guys tomorrow.
he's like just but now he just
Let's go 18 through 36 on 678. Yeah, we'll do evens.
Can we do odd?
So they're quicker. So this is page something again. 678.
So extend the hour.
Did anybody else have a submission for the extra credit problem before I call it a day?
oh wait, can I just tell you right now?
No. Nope.
Alright, hang on.
Oh, sorry. 678.
Hang on, I'm gonna email it to you.
Story of my life.
I'm gonna email it to you right now.
18. I got
Send.
No, I wasn't here Friday.
We started. We just went over a couple problems. We didn't do anything except for go over 11.3. So we just went over a couple of these and finished out.
Never collected.
No. I collected 11.2, so if you got 11.2, I'll get that. You can give me that today or tomorrow. It's not a big deal. Oh, you guys are gonna get so mad.
Oh, I know. It's probably,
This is gonna be so simple.
it's gonna be like, oh, if you know, add 2.
It's probably the
Oh,
same
wait,
order.
no, give me 1 minute. I guess one minute.
All right, I'm putting it up.
Give me 1 minute. Give me
Wait,
quick and on email. I don't know. Hold on. Let me just. Give me 1 minute. All right, I'm sending the email. Right.
Wait, are you playing up the right hands?
I am.
How many people
1
got it right?
second. Wait, hold on.
All right, I got the crazy Rooskies.
Yeah.
All right.
How is it?
I don't know.
Send it to.
Have you sent it yet?
Murphy at
Jeez. Nothing better than being a procrastinator. I'll tell you a story about that later.
I get it. That's funny.
Wait, what's the?
Oh, I got it. We just went over it.
All right. The answer is